Hello, everybody, and welcome to Tim Time Projects, where our project today will be taking a look at an old low-pass filter I found uh, in a box of stuff that I collected from a Silent Key years ago. And I just thought, let's take a look at it and see how it works. So let's dig in.
Restart. Okay. So it says low pass filter. I got this from a. I'm going to take it apart and see exactly what it is. I got this years ago from a co-worker's grandfather who passed away, and he was a ham, so I guess somewhat of an estate, Silent Key, and a little bit south of Pittsburgh in McKeesport. This was some of the items that I got. A lot of the way older stuff. Didn't have room for a lot of it. So what do we have here? It looks pretty much like a network of. Can you see that? Yeah, you can see that. I see inductors, a couple of capacitors here. And he has it separated. He has the different sections separated. That's kind of interesting. Not sure why he has, if there's any purpose for him to be it's a little bit of an angle here or not, but and he used insulation in between where he runs the wire in between. Used insulation. Looks like they're hand wound coils. Another capacitor here, another capacitor back there. So quite a nice piece of work. The solder joints look really well, and that's pretty neat. So we can try and pass the signal through it and see what happens. So I'm going to get things set up for that. Alrighty, so you have the signal generator here going into the A lead here, and then coming out and going to the oscilloscope over here. By the looks of it, by its design, I don't think it matters input or output. It looks pretty symmetrical the way it's built. So let's see. So let's do autofocus and set itself up. So here we're looking at a 1000 hertz signal. These glasses are not what I usually use. Yeah, 1000 hertz. And here I'm seeing 1000 hertz. We're not going to worry too much about matching the input and output because we already know that things change in between the two, especially when I lean on stuff. But let's see when we go up in frequency what happens, or how soon it happens. Being as he was a ham operator, I'm going to assume this was probably functioning in the HF bands. So there's one. We'll just see. Hopefully you can see through my arm. Alright, so might have to bust out the other scope because we're not going to get much above 30 with this one. I'm sorry, not the other scope, the other signal generator. And I'm assuming, I don't know. Oh, that this was to keep signals in the HF band and not be elsewhere. So let me see what else I can get hooked up here.
All right, so here we are. We have to use the HP function generator for this, signal generator actually, for this this test because the little signalant won't go past 30 megahertz, and my calculations are correct. This low-pass filter was built for the ham HF bands, and that would be like right up into the 30 megahertz band. Not the 30 megahertz. That would be right up into the 30 megahertz area. 29 being the highest, 29.6 or something. No, I had 29.7 or 8, I don't know. But and then anything past that would be 6 meters, and I think this might date back to older days, but anyhow, with this I can go all the way down, and I can do rough and coarse adjustments. So I can do 21 megahertz. I have it set at 1.5 volts, so that would be RMS, I'd imagine.
Yep. Auto calibrate. There we go. So here we have 20 megahertz. And that's telling me about, oh boy, 285 millivolts. Let's make sure we get that on the times 10. And again, not that this is going to matter too much to us. AC coupling, we're using a times 1 probe. So let me put the probe back to times 1, and there we go. Get rid of this. Turn that back on. Alright. Here we go, about 1.8 volts. So it's going to end up being similar to what that was, I believe, but it doesn't matter. So that's 20 megahertz. So I'm going to jump the frequency up. The highest we could get with that was 30, so we'll try 40 megahertz here. 40 megahertz. Alright. I don't see anything on that scope. Let's try this. Let's try 30 megahertz. 30 megahertz. The signal did come back, so we're gonna have to maybe try and sweep it. Let me try it. Let's just see what. We'll say 35 megahertz. 35 megahertz. 38 megahertz. Oh, it's almost gone to 38. So that is quite an effective filter, I'll tell you that. Nothing after the outside of the HF band can get out of that. I don't know if I'll be able to put both these on the screen. So there's 38 megahertz, 28, 18, 8. No, I have to go down. Do 4 megahertz. That's 300 megahertz. That's nothing. 29 megahertz. We still have pretty good. It's starting to cut off there. Most hams don't even go up that high. Most hams usually don't go up much past even 15 meters, which is 21 megahertz. So like fine tune 21 megahertz. But they certainly don't get up unless they're on a 6-meter rig, which that's actually not even HF anymore. We'll ask Copilot. I'll ask Copilot. Let's see. Okay, I said, would a ham radio operator use a low-pass filter on a high-frequency transmitter? Yes, a ham radio operator might use a low-pass filter on a high-frequency transmitter. HF transmitter can produce harmonic frequencies that interfere with other communications and devices. A low-pass filter helps in suppressing harmonics. It reduces the transmissions of unwanted harmonics and frequencies. Regulatory compliance, preventing interference. So back in the old days, it would keep it out of the TV band. I think that used to be a big thing with ham operators back in the day when when televisions received their signals over the air rather than now everything's cable and digital. So, all right, well there you have it. That's this pretty neat looking Homebrew low pass filter and how effective it is. That's really something. Thanks for watching.